Okay. Now, B part 3, lecture 9. Legendre Transform of X, f of xy to G, attention now, px and y. Y here remains fixed, you see? The only x will move to p of x. Now, note that dg is equal partial of g respect to px, dpx plus partial g respect to y dy. So this dpx and dy, this implies that g can be a function of px and y. In other words, should be is better. Should be function of px and y. So this dpx and dy implies px and py as an independent variable of the dependent variable g. So let's consider f, x, and y. The differential of f is partial f respect to x dx plus partial f respect to y dy. Respect f respect to y dy. So this is px dx plus py dy. Again, dx and dy, okay, implies that f is a function of x and y. That's important here. The differential here implies that the function must be dependent on x and y, you see? Now, trick. To obtain g as a function of px and y, that's what I want. I want this. You see later why I want this function, only function of px, and y remains fixed. Now, that's a trick. I plug g is equal x px minus f. This implies that the differential of g is differential of this product, x and px minus df, in this case. So I substitute df here on here. You see? Let's put a color just for you, just to clarify. So this is df over here, okay? And this is df over here. I substitute df there. And also I applied, you see, the differential of a product, okay? This will be, this case, x dpx plus px dx. That's this part over here. Minus, you see, this is f. This is f. You see, this is df I substitute here, okay? Now, dg is x dpx minus py dy. Why? Because px dx cancel with px dx over here. So that's left only x dpx minus py dy. That's what I want. You see, dpx over here and dy over here. So this implies that g must be a function of px and y. You see the differential here. Now, attention now. I only obtain x can be obtained only if it is possible from exactly this definition over here. So this is a definition, okay? So I can, if it is possible, I can express x in terms of px, in this case, px and y. So this over here is a trick to obtain g, function of px and y. as I said, you see ahead why this is a very, very, very important relation, okay, for G function, let's say, a very important function, just to move to Hamiltonian H via Legendre transformation L. Now, the Lagrangian L is a function of Q dot and Q, and H is function of P and Q, is Hamiltonian. I want to move to apply the Legendre transform from L to H. Now, Q here, you see, this is an abbreviation of Q dot I. Q dot, abbreviation of Q dot I, Q, SQI, P, SPI. I is equal 1, 2, 3, and N. So when I have many generalized coordinates, you see, I can apply the Lagrangian. So we see from here, okay, that f, x and y, using the Legendre transform to obtain G function of px and y. You just derived here, you see? I start from f, okay, and obtain G function of bx and y. Again, y remains fixed. Now, that's what I want, you see, to emphasize the analogy, okay, between F and L, the Lagrangian. X is Q point, Y is Q. Now, G is H, Px is P, Y is Q. So this is generalized coordinates, P is the momentum. Define, attention now, do you remember partial F with respect to X? This is partial L with respect to Q dot. You see, X here, Q dot. So this is analogous to partial F with respect to X. You see the blue one? You see the corresponding L here. You see the blue one. So then, hence I can express the Hamiltonian PQ in terms of the Lagrangian. You see, you see the correspondence here and write down this is corresponding to the G. See, that's quite easy. This is corresponding to F. So this is the relation between Hamiltonian and Lagrangian obtained by the Legendre transform. You see, we'll continue this, and don't forget, my goal is express the Hamiltonian in terms of the Lie bracket. See, that's and also you see some important properties of the Hamiltonian mechanics or Hamiltonian physics. You see in the next videos.